The two basic building blocks for planar geometry are the point and the line. The line has two common properties, given by the familiar expressions straight line and the shortest distance between 2 points is a line. But when we replace R2 with an arbitrary surface in R3, then straight lines in the Euclidean sense clearly no longer satisfy the properties of straightness and shortest distance. They may not even lie entirely on the surface. For example, on a sphere, the curves of shortest length are actually arcs of great circles, which are certainly not straight in the Euclidean sense. On arbitrary surfaces, the analogs of lines are called geodesics. This summer, I have been working on calculating and displaying geodesics on surfaces. One surface I have studied is the familiar torus of revolution. This surface has positive curvature around the outside, negative curvature around the inside, and zero curvature along two circles, one on the top and one on the bottom. In the following animations, we will see a geodesic spray of 16 equally spaced geodesics starting at 3 different points and propagating outward. In each frame, the graph on the left represents the geodesics on the surface itself, and the graph on the right represents the preimages of the geodesics in the parameter space. The blue lines represent the boundaries of the fundamental region of the parameterization. In all 3 cases, the smallest squares in the grid have sides of length 2 pi. Here we see the geodesics starting from the point 0, 0 in the parameter space. This represents a point on the outer rim of the torus, in the region of positive curvature. Notice how the positive curvature focuses all except 2 of the geodesics back towards each other, so that only 2 rays cross the inner circle. Now we are looking at the geodesics starting at the point pi over 2, 0 in the parameter space. Here, the point is on the top circle of the torus. So at this point, the curvature of the torus is 0. This time, 6 of the geodesics escape the focusing effect and cross the inner circle. Finally, we see the geodesics starting at pi 0 in the parameter space. This point lies on the inner circle of the torus, where the curvature is negative. As you can see, there is no focusing effect at all. The programs used for the torus can also handle more complicated surfaces, such as the ones shown here. The programs used to make this video were written in Mathematica and implemented on Next, Sun, and Iris workstations. The images were generated using Mathematica and GeomView.
The thing you see on the screen is called an orbifold. More specifically, an orbifold is a Hausdorff space Q such that every point x in Q has a neighborhood homeomorphic to Rn modulo some finite group, perhaps different for different x. An orbifold is a good orbifold if it has a covering which is a manifold. The following theorem is true for two orbifolds. The singular locus of a two orbifold has only three possible types of local models. The first type is a mirror R2 modulo Z2, where Z2 acts by reflection through the line. Whenever you try to go through the mirror, you reflect it back. The second type is a cone point of order n, R2 modulo Zn, Zn acting by rotations of order n. The fundamental domain is the region between two rays, meeting at the angle 2 pi over n. But the rays themselves are also identified by a single rotation by 2 pi over n. When we glue them together, we get a cone. The last type is a cone reflection of order n, R2 modulo D2n. D2n is generated by all reflections in two lines, which meet at the angle pi over n. This looks like two mirrors, with the angle pi over n in between. The so-called convex notation let us classify all two orbifolds. For example, the monster orbifold is circle-circle, 2, 3, infinity, star-star, 3, 4, infinity, star-infinity. We can easily define an Euler number of an orbifold. It happens that each good orbifold has as its universal covering one of the following fundamental spaces. Euclidean plane, if its Euler number equals 0. Sphere, if its Euler number greater than 0. Hyperbolic plane, if its Euler number is less than 0. Because of this theorem, we can easily define the metric and the geodesics on each good two-dimensional orbifold, carrying them from the universal covering. My aim was to find a nice planar visualization of geodesics inside the orbifold. I restricted my attention to two orbifolds which have only finite number of cone points, including the cone point of order infinity. The basic idea how to implement the visualization is to find the conformal mapping from the orbifold to the fundamental domain of the covering. Draw the geodesic in the covering while mapping it back to the orbifold. The hardest step is to find the conformal mapping from the orbifold to the covering. In all 12 Euclidean and spherical cases, it is possible to do it. For example, the only technique you need for any Euclidean orbifold is the Schwarz-Christoffel formula and Schwarz principle of reflection. Unfortunately, for a general hyperbolic orbifold, the problem is extremely difficult. I implemented the hyperbolic case 2 to 2 infinity, where you have 3 cone points of order 2 and a cone point of order infinity. Here is the universal covering of this orbifold. The program I wrote this summer draws the unique geodesic, starting from a given point in a given direction, like this. Let's look at some features of this orbifold. This is a geodesic that goes almost directly into the cone point of order 2. As we expect, the geodesic turns around by almost 360 degrees. This happens because the complete angle around the cone point of order 2 is only pi. In general, if the geodesics come close to the cone point of order n, it tends to turn around this point n over 2 times. Here we have a geodesic that balances between two cone points several times. This geodesic might seem more complicated than the others, but almost all of them eventually become complicated. Almost every geodesic returns to the neighborhood of the cone points infinitely many times. I just track a geodesic until it first leaves some big circle around the origin. Here are a few more examples of interesting geodesics. You can use orbifold pinball programs through the World Wide Web.
My project this summer involved looking at rational maps from a sphere, such as the one you see here, to itself. Many of the maps I considered had the symmetries of the icosahedron. In algebraic terms, this means they commute with the rotations which leave the icosahedron invariant, such as the ones you see taking place now. Notice that whenever the icosahedron stops, we see exactly the same picture as when it first emerged from the sphere. In practical terms, This means that the entire action of the rational map is contained in a small part of the sphere, and any pictures which result from these maps will also have the symmetries of the icosahedron. Notice that whenever you rotate the icosahedron in a way that leaves it invariant, the set of vertices, the set of midpoints of edges, and the set of centers of faces each remain invariant. The rational maps I looked at were each tied in to at least one of these sets of points. These maps were constructed in such a way that almost any starting point converged to a period 2 attractor under iteration. In the pictures that follow, points on the sphere are colored according to how quickly they converge to one of these attractors. This picture comes from the map associated with the vertices of the icosahedron. Green corresponds to points which converge quickly, while blue points converge more slowly. The faces of a dodecahedron, which is dual to the icosahedron, are represented in the 5-pointed stars. This picture results from the map associated with the face centers of the icosahedron. On this sphere, purple points converge quickly, while yellow points converge more slowly. The stars on the previous sphere have been replaced by triangles corresponding to the faces of the icosahedron. This picture comes from the map associated with the edge midpoints of the icosahedron, which are also the edge midpoints of the dodecahedron. Blue corresponds to points which converge quickly, while again yellow corresponds to points converging slowly. As in the first picture, the faces of a dodecahedron can be seen in the blue pentagons. This picture comes from a member of a 1-parameter degree 31 family of maps with icosahedral symmetries. In addition to the stars on the sides of a dodecahedron, there is also threefold symmetry in the basins of attraction for this map. In this picture, as well as in the next one, red points converge quickly, while yellow points converge slowly. Here's the picture associated with another member of the same degree 31 family of maps. On this sphere, we can see both 5-sided and 6-sided stars interlaced as in a soccer ball, giving both 5- and 6-fold symmetry. These last pictures show what happens to a family of maps with octahedral symmetry as its parameter varies. Green points converge quickly, while darker points converge more slowly. Look for the octahedron and its dual, the cube, on the sphere as it evolves. As we go through the parameter space, the evolution may appear to be slowing down. In fact, however, we are accelerating through the space as the evolution proceeds.
Welcome to the 3-sphere, the surface of the unit sphere in 4 space. We can view this space, much as a flatlander would view an ordinary sphere, by shining a light down from the top of the sphere and viewing the shadows it casts on the plane. Notice how the equator's shadow is circular, and the longitudes cast shadows which reach out to infinity and twist back around. With these observations in mind, let us move up a dimension to view the 3-sphere. Similarly, we can put a 4-dimensional light at the top of the 3-sphere and look at the shadows the great circles cast into space. We see similar patterns, though now the shadow of the equator is a sphere and 3 lines of longitude meet at the center. Look at what happens to the shadows when we rotate the 3-sphere around an arbitrary axis. Pretty wild, isn't it? Let us look at some points in this space, say +1 on each of the 4 axes. Remarkably enough, it is possible to define a law of multiplication for points in this space. The blue point is the result of multiplying the 2 green points. Notice that the same 2 green points multiply to produce different blue points. The order in which they multiply matters. Since multiplication is non-commutative, if we multiply by an element p on the left and p inverse on the right, we get a result which is non-trivial. This important operation is known as conjugation. As a demonstration, we will conjugate the gold circle by the blue point as it moves along the axis. Conjugation acts as a rotation on the gold circle. Notice that the gold circle rotates twice as the blue point traverses the axis once. Now we have picked out those blue points which would rotate a triangle onto itself, that is, the group of rotational symmetries of a triangle. There are 6 points because each rotation in this group is represented by 2 points in the 3-sphere. Remember, our gold circle rotated twice. These are the points representing the rotational symmetries of the tetrahedron. There are 12 distinct rotations in 3-space which bring a tetrahedron to itself. Any rotation in 3-space corresponds to 2 distinct points in the 3-sphere. So we see 24 points in this picture of the tetrahedral group. You can see how these points regularly fill the space of the 3-sphere, especially as seen here from the insider's point of view. Finally, what we've all been waiting for, supreme among finite rotation groups, the 120 points representing the symmetries of the icosahedron. We have escorted you through spherical geometry, where points can represent rotations and many other things are possible. This exceptional space, one of very few low-dimensional spaces with a full group structure, has many fascinating properties. Find out more in the math library nearest you.
In mathematics, one is often interested in looking at geometries that live in more than 3 dimensions. Our goal here is to present a few tools that one might use to visualize these higher dimensional objects. The first tool is one with which you are intimately acquainted. We can move around an object to view it from different sides, as we have been doing with this icosahedron. Our second tool is also a familiar one. If we shine a light at a 3-dimensional object sitting in front of a flat wall, it projects a 2-dimensional image onto that wall. If we spin the room while fixing the object, we get different projections. Let's examine this helix as we project it into a 2-dimensional space. We have included color-coded axes to help us see what is going on. The x-axis is colored red, the y green, and the z blue. Note how one coordinate axis is projected out of the picture and another is projected in. Unfortunately, this process robs us of valuable information. Let's look at the beginning of this sequence again. In this picture, it appears that the helix possesses a self-intersection, yet we know that this is not the case. To take care of this problem, we bring in our third tool. Here we have colored the helix according to the rule that points lower in the direction of the white line are colored purple and blue, while those that are higher are colored orange and red. How does this help us to interpret our other picture? The point of apparent self-intersection can be explained away by means of the coloring. Where the projection meets itself, one branch is purple while the other is orange. This means that these 2 branches of the curve are separated in the direction which is no longer visible. Now let's use these ideas to explore a higher dimensional object. Here are 6 images of a projection of the 6-dimensional 2 surface known as the Veronesi surface. We have included coordinate axes color-coded red, green, blue, white, yellow, and cyan. Let's apply the same color scale to this object that we used on the helix, coloring points in this picture based on their position in the first coordinate direction, here by their position in the second, the third, fourth, fifth, and sixth. Now prepare yourself to explore this surface as we change both the projection and move our perspective. Remember, the object itself will not move, only the manner in which we view it.
This summer, I studied a question that has mystified me for a long time. What makes the pattern of colors on soap bubbles? As it turns out, this is already well understood. Let's first look at how a flat soap film reflects light of just one wavelength. The reason soap films are colored is because their thickness is on the same order as the wavelengths of visible light. Light rays reflected toward us from the top of the film interfere with rays that pass into the film and reflect toward us from the bottom. These rays may interfere destructively or constructively, depending on the thickness of the film and the wavelength of the light. For a film with constant thickness in monochromatic light, as shown here, the phase difference between the two interfering rays depends on our viewing angle. This causes the bands of constructive and destructive interference we see. For different wavelengths, the interference bands phase in and out at different places. If we combine the bands contributed by all of the wavelengths of the visible spectrum, we see the colors of a soap film. Since a computer can't add an infinite number of things, I have chosen 6 representative wavelengths to generate this and all of the following pictures. Now, let's look at a soap bubble. As a first step, we consider a bubble with constant thickness. The edges of the bubble appear brighter because as we look at a film more obliquely, it reflects more light. This is called the Fresnel effect. I haven't said anything about how a soap film affects the light it transmits, but all you really need to know is that it works exactly the opposite of reflection. In this picture, light has been added behind the bubble. The edges of this bubble are darker due to the Fresnel effect on transmitted light. This bubble has constant thickness, which is not very realistic. The thickness of a real bubble is not constant. One cause of variation is gravity, which drains liquid towards the bottom. In this picture, for example, the thickness of the bubble is adjusted to increase linearly from top to bottom. The lighter circle inside the bubble is the reflection of the shape of our light source. Evaporation causes a slow decrease in thickness in all parts of the bubble. In the following animation of a thinning bubble, I have added window and ceiling lights to show both reflection and transmission effects. Of course, the surface of a real bubble is very turbulent, causing rapidly changing swirls of color. These are really the most interesting feature of a bubble, but unfortunately, I haven't yet found any good way of modeling them. These pictures were generated with a ray tracer written in C, which is available by anonymous FTP from the Geometry Center. Some of the following objects were generated by Ken Brackey's surface evolver, which is also available.
Josephson junctions are superconducting circuits which display unusual properties. The circuit has a small gap which resists electrical flow. The current, however, still flows because electrons manage to tunnel in pairs through the resistor. This tunneling effect has interesting dynamics. The purpose of our summer project has been to further understand these dynamics by studying the ordinary differential equations describing the coupling of two Josephson junctions.
Let's first see how a continuous dynamical system works by looking at a pendulum. There are 2 parameters that affect the motion of a pendulum: torque and dissipation.
This bifurcation diagram describes the dynamics of the system. Each region has its own characteristics. For example, for this parameter value, the pendulum can either wind down or reach a limit cycle, depending on the initial conditions. At sufficiently low torque, the system has 2 fixed points, a stable one and an unstable one. The last important features of these dynamical systems are manifolds. These are spaces that extend from the fixed points. They are important tools in analyzing how the system acts. Now let's return to the system of two coupled Josephson junctions. Here, we also have two parameters: the amount of current in the circuit and the capacitance of the circuit. Unlike the pendulum, however, the phase space for the system is four-dimensional. To visualize orbits, we look at several two-dimensional projections. This system has four equilibria: a sink, where everything approaches the point; a saddle with two stable manifolds and two unstable manifolds; and two saddles with three-dimensional stable manifolds and a one-dimensional unstable manifold. This system has many bifurcations. This sketch in phase space shows lines of connecting orbits. This is the line we calculated and studied this summer. It is a line where a 1-3 saddle connects with itself. What happens is that an orbit goes out along the one-dimensional unstable manifold of the equilibria and returns into the three-dimensional stable manifold of the same point. This is a heteroclinic connecting orbit.
We also studied limit cycles and their bifurcations in parameter space. For example, at the heteroclinic connecting orbit, the limit cycles cannot be found by numerical integration, and all attempts to find them end up in the sink. One interesting set of bifurcations found is the period doubling cascade. As one parameter is decreased, the periods of the limit cycles double again, and double again to infinity. Here is a different two-dimensional projection of the four-dimensional phase space diagram of the cascade. By taking a certain three-dimensional slice of the limit cycles, we get fixed points that correspond to the period. Using GeomView and these slices for many parameter values, we generate a picture representative of the cascade. This picture is analogous to the well-known period doubling bifurcation for the logistic map. Also, it is worth noting that the ratio of the distances between bifurcations in the parameter space converge to Feigenbaum's number, although this will not be explained. For some other parameter values, there are different interesting bifurcations. Zooming in on an area of high contrast, as one parameter is decreased, the period doubles, undoubles, doubles again, and then undoubles again. Although we cannot yet explain this phenomenon, a tangential result is that the eigenvalues of the nearby saddle satisfy the requirements for the Shilnikov theorem. This implies that there are limit cycles of arbitrary period nearby, although they might be unstable, and thus cannot be found by numerical methods.
This program discretely models the behavior of ants who are always and only aware of their immediate predecessors. The user draws the curve along which the first ant will travel at a constant speed. A green dot marks the initial point, a purple dot denotes the final point, and orange dots represent ants. Each subsequent ant finds the location of the ant immediately preceding it and then heads in that direction, drawing the resulting trail. The user can specify, within limits, how frequently ants are created, how often they re-evaluate their choice of direction, and the size of each step. Execution stops when the last trail completed is sufficiently straight or when there are no ants left to follow. The algorithm is based on the continuous model in Alfred Bruckstein's article, Why the Ant Trails Look So Straight and Nice. The program is connected to the dynamic kit on a NeXT computer. As these more complicated curves evolve, here's a brief sketch of some of what I have learned about ants' actual behavior. Different species of ants use varying forms of orientation depending on the situation. Some of the cues utilized are gravity, odor, and vision, which includes memory and awareness of light polarization. According to the book The Ants, in order to assemble workers for joint efforts, various species employ idiosyncratic combinations of touch, stridulation, and chemical cues. In fact, the chemical trails of the red imported fire ant Solopensis invicta not only lead ants to the location of food, but also indicate the quality, since a worker only leaves a trail after picking up food. If the ant doesn't reach or doesn't like the food, the scent trail is not reinforced. In contrast, there are species where the recruited group will only reach the food if the original ant is present. Moreover, in some, only one ant, which must be in almost constant contact with the leader, can be recruited at a time. The model in the computer program is closest to that of mass communication, as in the fire ants, where the initial ant does not always have to be present. Another version of the computer program allows ants to orient by odor alone. After each move, every ant deposits a dot of pheromone that will diffuse and evaporate over time. Each ant uses a comparison of the amount of pheromone at the tip of each antenna as the basis for its direction. The interface is the same as before, except for the extra variables of evaporation rate, diffusion rate, the size and concentration of the pheromone deposited, the largest possible radius for the sense active space, the minimum concentration of odor an ant can detect, the antenna length, and the angle between the antenna. In the real world, ants would not use either of these idealized models. Instead, they employ a combination of senses.
Genetic programming is a computer science technique based on the process of natural evolution. The genome encodes a possible solution to the problem under investigation. It could represent a formula, algorithm, or program. Random mutations and crossbreeding of the parents are done to generate more gene sequences. A fitness function judges how well sequences solve the problem. Top scores are used to create the next generation. This summer, I created a toolkit for exploring genetic programming problems which have no natural fitness function, such as images and fractals. This is the interface for the program. The problem module to be used is selected here. This grid presents the current generation of images. Double-clicking chooses the one to be mutated into the next generation. The inspector examines the currently selected object. This window is a history of what portion the problem space has been traveled. One can go back to a previous generation by double-clicking. Images are created by a function mapping from R2 to R3, where the range is red, green, and blue triples. Image-generating functions are created by compositing simple functions together. Expressions are mutated by walking down the tree representation of the expression and deciding at each node whether to mutate or not. If the node is to be mutated, then any of 4 actions takes place. Option 1. A node from below is brought up to replace the current one. Option 2. The node is pushed down a level and a new node added. Option 3. The function of the node is changed. Option 4. The node is replaced. After a few generations, extremely accurate images are generated. Here are some examples of images found. Genetic crossfades can be generated by taking weighted averages of different subexpressions. Here are some example crossfades. The toolkit is designed so new problems can be quickly added. So far, iterated function system fractals have been investigated. Here are some interesting IFS crossfades.
One can create different three-dimensional manifolds by gluing together opposite faces of regular polyhedra. My project this summer was to create a program that would simulate the behavior of geodesics in these manifolds. Specifically, I studied the 2 different manifolds created by gluing opposite faces of a dodecahedron. Let's first look at the three-dimensional manifold formed by gluing together opposite faces of a cube. This is the simplest closed three-dimensional manifold to understand. It is called the 3 torus. In the 3 torus, objects that exit through the top of the cube would re-enter from the bottom. Here is how geodesics, the equivalent of straight lines, would appear in this new three-dimensional space. Looking at how geodesics propagate gives us an intuitive way to visualize how things would look in these 3 manifolds. We cannot see the whole of these spaces since the space we live and see in is three-dimensional itself. One thing we can understand, for example, is that the 3 torus has Euclidean geometry. This is because the edges are identified together 4 by 4, so when they come together, there are 360 degrees of space around each edge, the same amount of room as in Euclidean space. The manifolds formed from the dodecahedron are more difficult spaces to visualize than the 3 torus. This is because the opposite sides of a dodecahedron do not line up. To glue them together, a rotation must be performed. Depending on the angle of rotation, 2 different spaces are created. The Poincare space is created when one rotates a face 1/10 of a turn, or 36 degrees, before performing the gluings. In the Poincare space, the edges come together 3 by 3. The dihedral angles of a dodecahedron are 116.5 degrees, so when 3 edges come together, there is only 349.5 degrees of space around the new edge. This pinching makes the Poincare space what is called an elliptical space. Let's see how a geodesic behaves in the Poincare space. The Seifert-Weber space is created when one rotates each face 3/10 of a turn, or 108 degrees, before performing the identification. Here all the vertices are sent to one point, and the edges come together 5 by 5. So there is now 582.5 degrees of space around each edge. This is more than in Euclidean space, much more in fact, and because of this, the Seifert-Weber space is what is called a hyperbolic space. Let's see how a geodesic behaves in the Seifert-Weber space. The behavior is much more chaotic. Here is a beam of geodesic rays in the Poincare space. And here is a beam of geodesic rays in the Seifert-Weber space. This program was created on the next computer using Mathematica, and the graphics were done in GeoMView.